In this video, we're going to start talking about data analysis and probability theory. So far, everything we've done has been more of building models and deducing some consequences based on the assumptions built into the models. So mostly what we've done is we've started from some cause, and then we deduced a set of possible outcomes or effects. And so the mode of reasoning we've used so far has been of a deductive nature. And I want to contrast this to the other mode of reasoning which we're now going to use, which is where we start from a set of observations or effects, and we reason the other way and we try to infer what are the possible causes. And of course we'll have multiple causes that are consistent with the observations. And so this mode of reasoning is called inductive reasoning. So for deductive reasoning, there's calculus of logic. So Boolean logic allows us to combine the truth or falsity of various propositions and combine them and determine the truth or falseness of various statements involving combinations of those statements. So for example, one that Jane's used is that we have the statement, all men are mortal, Socrates is a man, and then from this we can infer, therefore Socrates is mortal. So this is a logical statement that follows from the rules of Boolean logic. So this form of logic is more or less what we've been using without explicitly stating when we've been going through our modeling efforts so far. And that's usually the kind of modes of reasoning that people associate with pure mathematics, for example. But of course, mathematicians don't use only deductive reasoning. They use mostly inductive reasoning to discover new theorems and discover what the proofs are. And there's this book by Polya, Mathematics and Plausible Reasoning, and Polya goes through all these various modes of thinking that allows us to reason and make inferences, because it's an important way of thinking. And mostly in the sciences, we're almost always working with inductive reasoning. So we have some theories, multiple theories, and we collect some data, and then we want to decide on the relative plausibility of different theories based on our observations. And so this is what we're going to start working with in this part of the course. And the book that we're going to follow is the book by Sivia and Skilling called Data Analysis, a Bayesian Tutorial. And so this is a nice book because it's full of practical ways in which we can use probability theory to make inferences about data and the state of the world or various propositions. So for example, we'll learn how to fit a straight line through some data and estimate the slope and the intercept and assign error bars to the slope and the error intercept, and how the slope and the intercept are related to each other, so the joint probability for these parameters, as well as comparing the probability of various theories or models, the relative probability. So this is the kind of stuff that's described in this book, and we're going to follow this. So the philosophy adopted by this book is pretty much consistent with the one in this book by E.T. Jaynes called Probability Theory, the Logic of Science. And so what Jaynes does in this book is he extends the rules of logic, where we reason about statements or propositions that are either true or false, there's no in between, extends it to cases where we have incomplete information to decide for certain that a statement is true or false. What we want to be able to do is assign a plausibility to various statements so that we can compare them and say, well, A is more plausible than B, B is more plausible than C, and so on. So this is the framework for thinking about logic in the presence of incomplete information. And so I want to recommend this book to you. You should get a copy, put it by your bedside, and study it during the course of your PhD studies. And I think if you study this book, you'll definitely become a better thinker, more logical and more clear thinker, and probably a better scientist. So it's definitely worth reading. And it's fun to read because it's written in the form of a polemic. So Jaynes kind of goes on a rant against what he calls the school of orthodox statistics, or the methods of frequentists. So at this point, it's probably useful to give a little bit of history on the subject. So the mathematical theory of probabilities probably started with Bernoulli, who used it to assign probabilities for games of chance. So card games, rolling dice, or flipping coins, stuff like that. And I guess there's also Bayes. Reverend Bayes is an important contributor to this because he came up with what is called Bayes' theorem, which allows you to update your probability about the truth of some statement based on new information. So Bayes' rule is a major part of Jane's book and a major part of Sylvia's book on how we analyze data. But Bayes never really used this theorem very much from a scientific point of view. Most of the contribution come from Laplace. So Laplace in the early 1800s rediscovered Bayes' theorem and came up with the mathematical methods for applying probability theory to analyze data. And so they point out in this book that, for example, that Laplace, for example, he said, is a bet of 11,000 to 1 that the error of this result, being the mass of Saturn, is not 1/100th of this value. So he's able to give odds on the chance that the estimate is correct. And so I was curious about this, and I went online and I looked up first the mass of Saturn, and I looked up Laplace's book, and it's in French. It's the Analytical Theory of Probabilities, and in the introduction he quotes what the mass of Saturn is. So it's 1/3,512, that of the mass of the Sun. And he also gives us, if you read down, where's my mouse? Down here, the mass of Jupiter. And what's important is that Laplace also gives us an error bar. And he says that over here, he says the odds are 11,000 to 1 that the true mass of Saturn falls outside a range that's 1/100th of the quoted value. So he says essentially that the probability that the true mass of Saturn, that the relative error is more than 1%, the probability of that happening is 1/11,000. So he gives a very clear quantitative estimate for his uncertainty. For the case of Jupiter, he says that the odds that the error is more than 1% is 1 in a million, right? So let's have a look at these error estimates and see how they hold up with the test of time. And so I've copied those down for here. This is the estimate that Laplace gives in his introduction for the mass of Saturn, and it's 1/3,512 times the mass of the Sun. And he says that the error is the probability that it falls outside of the range of 1/100th of this quantity is less than 1/11,000. And so if I convert this into a decimal, this is his error bars, 2.847 times 10 to the minus 4 plus or minus 2.8 times 10 to the minus 6. And then I Googled what the current estimate for the mass of Saturn is, and I get 2.857. So this is an error of, or the difference I should say, between these two estimates is 1 times 10 to the minus 6. And that falls within his error estimate. And so in the case of Saturn, Laplace would have won his bet. But in the case of Jupiter, that wasn't the case. So I Googled the current estimate for the mass of Jupiter, and I got 9.543. And so the error is 2, or the difference, I should say again, between the current estimate and Laplace estimate is 2 times 10 to the minus 5. And whereas his error bar is plus or minus 9.337 times 10 to the minus 6. So this is bigger than this, so it does fall outside the range. So despite the fact that Laplace had given the odds that the true mass would fall outside the range to be 1 in a million. And so, of course, 1 in a million is not certainty. The important point is that he's able to give probabilistic estimates for his error bars, and we're able to compare them and see with current measurements and see if we're improving or not. This calculus of probability to do data analysis that Laplace came up with, he shows in his book all kinds of possible applications, how you might use it in court cases to reason in terms of incomplete information, how you might assign probability to future events based on past events. It was based on what is called a Bayesian point of view. And so this philosophy of probability says that probability is something that has to do about your state of knowledge. So two people, for example, might assign different probabilities to the same events because they have different information. And to see, for example, how this works, if I take these two pens, one red, one black, and I hide my hands and I shuffle them around, and in one hand I have the red pen, and in the other one I have the black pen, and I ask you to assign a probability that the red pen is in my right hand, you will necessarily assign a different probability to that statement than I will. And the reason is that we have different information. I'm able to look and see if the red pen is in my right hand or not. So for example, I would assign 0 probability to it, but you probably would not have done that. And the reason is that I can see that the red pen is indeed in my left hand. And so this kind of reasoning is totally, makes complete sense. It's reasonable that probabilities have something to do with our state of knowledge about a situation. But for some reason, people got confused about this point of view in that it seemed very subjective to them, that different people might assign different probabilities. So they tried to, after Laplace, they tried to restrict the definition of probabilities to be something that about the world, something that you can measure. So for example, if you took a coin and you flipped it over and over and over again and you measured the frequency, so how often it comes heads, compare the total number of tosses, you would assign that number in the limit where you do the experiment an infinite number of times. That would become the probability of getting heads. So they limited the scope and the usefulness of probability by doing this to cases where you have repeated experiments. And from this mode of thinking, there developed schools of statistics of how you analyze data, which are called frequentist methods. And from this, I guess the developers of this kind of theory are Pearson, Neiman, and Fisher. These are some of the big names in this. And from this, you'll get ideas like unbiased estimators, confidence intervals, p-values, hypothesis testing. These are all methods that came out of the school of statistics called the frequentist, and what Jaynes in his book calls the orthodox statistics. And Jaynes kind of goes on a polemic on a rant about the difficulties of the frequentist method. So this idea of repeated experiments doesn't really make sense when in many cases where you want to reason and assign the plausibility to statements where it doesn't quite make sense to talk about repeated experiments. For example, if I had the statement, there was once life on Mars, it's hard to imagine how you might have an infinite number of experiments. I mean, there's only one Mars, and the evolution of the planets, the solar system, happens only once. We cannot redo the experiment. So, and yet we are uncertain about whether there was ever life on Mars or not. And so the frequentist view prevents us from reasoning, assigning plausibilities to such statements. And so Jaynes is going to try to argue very forcefully that the Bayesian view is the better method, and that is indeed the method that we're going to use in this class. So some interesting factoids about Fisher, who was one of the developers of the frequentist view of statistics, and somebody who helped revive Bayesian methods in the 1930s, which is Jeffreys. So Jeffreys and Fisher were both at University of Cambridge at the same time, and Jeffreys is a geophysicist, and he was an advocate for Bayesian methods. He wrote an influential book about Bayesian probabilities, and Fisher was a biologist, geneticist, and he did lots of experiments in agricultural experiments and analyzed the data to make, for example, you take a field and you treat it with some fertilizer, some manure, and then you want to compare which field grows better, what are the crop yields based on these different treatments. And so naturally, for Fisher, all the methods that he developed were very sufficient for his kinds of research, where he could repeat the experiment and from this they can derive sampling probabilities and derive error bars or uncertainty estimates. But for Jeffreys, who was a geophysicist, that's not so easy, right? You can't imagine recreating the Earth if you're analyzing earthquake data and you're trying to learn something about the internal structure of the Earth. You cannot create a whole ensemble of different Earths and repeat the experiments. But yet you still have uncertainty and you want to reason about uncertainties. Anyway, so why did I mention Jeffreys and Fisher is, I guess what I'm leading to is that the reason why we want to develop probability theories is to prevent us from not reasoning in a logical way. And I would argue that we're all susceptible to making mistakes in thinking. And so here's one example that comes from Fisher and Jeffreys. So Fisher, the biologist, never accepted the idea that smoking is a cause of cancer. He refused to believe that throughout his whole life. He was a smoker and he refused to believe the evidence. And there's a similar story about Jeffreys, who was a geophysicist, and apparently he never accepted the theory of plate tectonics, which has lots of evidence for it. So everybody can have some blind spots and we can all make some mistakes in reasoning. In fact, there's a famous book by Daniel Kahneman called Thinking Fast and Slow, and they give a lot of these examples of errors in thinking that people make. And so it's worthwhile to read this book so you can learn about all the biases and mistakes that people make when they think about situations that are uncertain. And so the way, to get back to Jane's book, the way the book is organized is that he imagines that we're going to construct a robot, and this robot is going to be fed some information, various propositions, and then the robot will use this information and decide on the plausibility, or the probability, what will turn out to be the probability of various statements, and be able to rank them and order them and say how probable various statements are based on the information we feed into the robot. And the reason we want to feed into the robot is that we now have to come up with the rules for thinking that this robot will need. So we'll program this in the computer, and then the computer will use these rules and decide on the plausibility of other statements. And so James will lay out a bunch of, I think what he calls it, desiderata, or things that we would want a robot to think, how we would want it to think, or ways of thinking that we hope that we would follow ourselves, because there are intuitively correct ways of thinking. And so in fact it's a very short list that he puts down, and then from this short list he derives the rules of probability theory as the only logical way of thinking about propositions that may be true or may be false, but we have incomplete information and we're unable to assign for sure a truth or a falseness to various statements. There's a kind of continuum based on our uncertainty. We want to assign a plausibility to it. All right, so we're going to start by first reviewing the rules of logic briefly, and then we're going to list James's robots, the desiderata for the modes of reasoning for it, and then we'll give the rules of probability theory. So that's the kind of the plan for the lecture. Okay, so the rules of logic are the following. And what we want to do is take various propositions. So for example, they could be A or B. And these propositions are going to be statements such as, for example, there was once life on Mars, or it's going to rain tomorrow, or my cat has 24 toes. And we want to reason about these probabilities in various combinations of them. So we want to have a formal way to combine various propositions and deduce the truth or falseness of these various combinations of propositions. And so the rules that we have for combining various propositions is the not. So for example, not A would be expressed like this with an overbar, and that would mean that, for example, if we make a little truth table for proposition A, so suppose that A is true or A is false, we have two cases, then not A will be true when A is false, and not A will be false when A is true. So the truth table will be like that. So the not just flips the truthness or falseness of the statement. We will also combine proposition using an and statement. So if we have, and this time we just write by multiplying them together. So it's a logical multiplication, logical product, and that logically is the way we think of and. So if we have A and B, and A can be true or false, and B can be true or false, I'm going to lay out all the possible cases. And on this side I will do the product A and B. So A and B is going to be true if both A and B are true. So in the first case that's true. In the second case, A is true but B is false. So it's not true that both are true, and therefore this is a false statement. And similarly this one is a false statement because A is false, and finally the last one where they're both false. So the and of A and B is also false. And then the next one we have is the logical or, and we write this one with a plus. And so that's the logical sum, which is read like an or. So if we have A and B, and on this side we will put A or B. So A or B will be true if either A is true or B is true, or both. So for the first case, A is true and B is true. They're both true. So A or B is also going to be true. In the second case, A is true but B is false. But for A or B to be true, we just need either one of them to be true. So in this case, since A is true, this is true. For the third case, A is false but B is true. So that's sufficient to say that A or B is true. And in the last one, they're both false, so then it's not true anymore that A is true or B is true. So this is a false statement. So here we have the three logical operations that we can use on A or B. And in fact, there's a theorem, it can be shown that these are all we need to construct any other proposition. So you might have some more complicated logical ways of combining various propositions, but they can all be broken down as some combinations of these. In fact, I think you only need the not and the and. You don't really need the or, but certainly not and or is sufficient. And to this, we're going to add a bunch of axioms or things we want to be true, and I'm going to state them here, and they're all going to be, I think, intuitively obvious that these have to be correct. So they have interesting names. The first one is Idempotence, and that says that A and A is equivalent to just A. So repeating the statement doesn't change, the proposition doesn't change its validity. And the same thing for A or A. That's the same as just A. And the other one is rule of commutativity. And that one says that A and B is the same thing as B and A. So the order in which we make the proposition doesn't make any difference in terms of the truth value. And similarly for the or statement. A or B is the same thing as B or A. And we also have associativity. And this one, we have A and B and C is the same thing as first A and B and C. And that's therefore the same as A and B and C. And for the or, we have A or B or C is the same thing as A or B, or C is the same thing as A or B or C. So it should feel like all these axioms are all obviously correct. The next one is distributivity. This one is a bit more interesting. But again, you can convince yourself fairly easily that this is a correct statement. So we have A or B and C is the same thing as A or B and A or C. And the other one is A and B or C is the same thing as A and B or A and C. So you should try to think of some examples to convince yourself that this is indeed correct. And the last one is duality. And this says that if C is a proposition meaning A and B, then not C is the same thing as not A or not B. And the next one is if D is A or B, then not D is the same as A and not D is the same as not A and not B. Right, so we can check these. So for D to be false, so not B, we need both. I mean, we need both that A is not true and B is not true. Then D also will not be true. So this is this statement, and this one, then not C. So not C will mean that it'll be sufficient for either A to not be true or for B to not be true. Then it will be the case that A and B is also not true. And then these rules can now be used to deduce more rules. So one example is if not B is equal to AD, then A and not B is the same as not B, and B and not A is the same as not A. So we're going to demonstrate these statements using these axioms. So let's start with the first one. So we have A and not B is the same thing as A and AD is the same thing as, now we're going to use associativity. It's the same thing as A and D. And now we're going to use the idempotence rule. So A and A is the same thing as A. So we have A and D. And A and D is the same thing as not B by the definition. And so that checks out for the first result. And now let's check the next one. So this one, we have B and not A is the same thing. I want to show that's the same thing as not A. So B is the same thing as A and D, and we have not of that times not A. So not A and B, we can use this rule over here, duality, to rewrite as not A or not B. So we have not A or not B and not A. Then we can use the distributivity. So we have not A and not A, or not D and not A. And then this one here, by the idempotence, this is just not A, or not D and not A. And then to finish things up, we're going to construct a truth table based on this. So if I start over here and I put in my proposition A and D, and I list all the possibilities, and then I'm going to construct first not A. So not A is going to be false, false, true, true. And then not D, also I can construct this one, will be false, true, false, true. And then I can construct not D and not A. So this one, if A is false and D is false, well, they're not both true, so this is clearly false. Here they're also not both true, these statements, so this is false. This one is false, but this one will be true. And then I can construct the last one, A, not A, or not A and not D. So that's the or of this column and this column. So they're both false, so this is false, both false, this is false. And the or, this one is true, this one is false, so as long as one of them is true, then this is true, and this one also, they're both true, so this is true. And now if I compare the truth table for this quantity, it's the same thing as this one, as just, no, sorry, not as this one, as this one, right? And that's not A, and so this checks out for this one. So this is the same as that. All right, so these are ways of using the rules of formal logic to decide on whether some statements are true or false. But now, following James, what we want to do is we want to extend these rules of logic to propositions where we don't know for sure if they're true or false. We just have some plausibility assigned to them, and we want to find a calculus for plausibilities. And so what James lays out are the rules for his robot. So James all right, so this is what we want a robot to follow these rules when he thinks. And so the first one is that we're going to say that plausibilities can be mapped onto the real numbers. So in other words, we want to be able to say that, for example, if A is more plausible than B, and B is more plausible than C, then A must be more plausible than C. So in other words, that there's a transitivity property of these plausibility assignments. And that ordering of the plausibilities is a property of real numbers, and so we may as well assign real numbers to them. So this example of transitivity, A is greater than B, B is greater than C, implies that A is greater than C. That's called the transitivity rules, and we want this for our plausibilities. And a counterexample, something that is not transitive, is, for example, the game of rock, scissors, paper, right? Rock beats scissor, scissor beats paper, and paper beats rock. And so in the rock, scissors, paper, if we were trying to argue with that kind of properties, we'd argue in circles. So I think it's reasonable that our plausibilities are going to be mapped onto the real numbers. And so we can then compare them the same way we compare real numbers. The next desideratum is one that we want our robot to follow common sense. And so if I write A condition on C, so C is the background information and A is the proposition we're reasoning about. So this bar here means the plausibility of A conditioned on some background information in C. So suppose we can reason about whether A is plausible or not. We assign a number to it, and we're going to say that that number is going to be less than a different one, another plausibility, where C primed is some extra information we added to C that made somehow A a little bit more plausible than it was before we added this bit of information. Now, if this is the case, and also we have another proposition B, which is indifferent to this extra information. So B, conditioned on A and C, is equally probable to B conditioned on A and C prime. So the extra information that made A a little bit more plausible has no influence at all on how we think on whether B is true or not. And so when this is the case, if these two properties are true, then we would like our robot to state that A and B conditioned on C is going to be less than or equal to AB conditioned on C primed. In other words, this extra bit of information that made A a little bit more plausible but didn't affect B should make A and B either more plausible or at least not make it less plausible. So it's a less than or equal. And this is follows common sense, and so we would like the robot to reason this way. The third one is consistency. And these ones are some sub-properties. And one is if there's more than one way to reason about a certain proposition, or more than one way arriving at a certain conclusion, then regardless of which way we take, they must all lead to the same results. So as long as we're following the rules correctly, if there's more than one way of analyzing the situation and they both follow the rules we're going to lay out, then they have to reach the same answer. And the next one is that the robot should take into account all relevant information. So the robot is not allowed to cherry pick the data. He has to use all the evidence he has. If it's relevant, he should use it. The robot has to be non-ideological, so he can't be like the news shows like Fox News or MSNBC, where clearly they have an ideological point of view and they're going to try to choose the news they present to their audience to try to convince them of a certain point of view. So we don't want our robot to reason that way. And similarly, when we're doing scientific analyses, we don't want to just choose some data in support of some hypothesis and neglect the rest of the data. We have to use all the information we have. So this is another rule. And then finally, C. Equivalent states of knowledge are represented by the same plausibility assignments. For example, if we just relabel the name of a proposition from A to B, then we should assign the same plausibility. So there shouldn't be any change in plausibility just by relabeling various plausibilities, for example. These last two here, these are basically the interface of how the robot would communicate with the field world. So how we would assign plausibilities. The thing that is maybe surprising is that these are all the rules we need to define a unique calculus of plausibilities, and these alone will produce, Jane shows in his book, they lead to the rules that we have for probability theory. So this will lead to probability theory. The only thing that we need is to have a scale, kind of a unit of how we measure things, and so what we're going to use is a scale from 0 to 1. So statement with a plausibility of 0, or now I can just use probability. A probability of 0 means something that is definitely false or impossible, and at the other end, 1 is a statement that is definitely true. So for example, the statement 2 plus 2 is 4, this would be assigned a probability of 1, whereas the statement 2 plus 2 is 5 would be assigned a probability of 0. All right, so that gives us the kind of the scale, and between that we can have a continuum between 0 and 1 of plausibilities or probabilities. So the two, and then these are the small list of desiderata for consistent and plausible reasoning, and they're all very sensible. Even shorter is the list of rules that we need to use probabilities. There's only 2 rules, and one is the sum rule, and it says that the probability of a statement A conditioned on some background information I plus the probability of not A based on the background information is equal to 1, so is certainty. Right, so if a statement A is either going to be true or not, and that's exhaustive of all the possibilities, so we get a definite 1 probability in that case. And then the other rule is the product rule. And this one states that the probability of A conditioned on B and I, so A conditioned on background information that the proposition B is true and all the background information multiplied, so it's the product rule multiplied by the probability of B conditioned on I, that is going to be equal to the probability, oh I should have put probability here, probability that A and B is true conditioned on I. And this together with the rules that the probability of a true statement is 1 and the probability of a false proposition is 0. And these are all the rules of probability theory. So using only this short rules, these 2 rules, we're going to be able to derive all the properties we need to do data analysis and make inferences from incomplete information.